Okay.
You lost your prologue, the family tree cousin thing.
Yeah, I lost the. I worked out the whole thing. I put in, the Simpsons family tree, at least enough of it to test all the features, and then I I forgot to save it before I closed my computer, so the tab was gone, and I go. I thought I saved it, but I didn't.
Yeah, I
Did.
installed the an actual like the I installed it on my computer,
Mm-hmm.
and getting used to the format, and I didn't quite realize how to compile, which is also save, and so I ended up closing my editor last night.
Oh.
Yeah, very annoying.
Yeah. I guess we have to whip out our cell phones and take screenshots of everything now. All right, so I am going to the folder where I saved that PL file. Let's see, where is it? It should be somewhere around here. Don't tell me. Oh, there we go. Cousins.pl. There we go. All right. Yeah. Well, the Simpsons names are, well, I mean, they're names from the Simpsons, right? I mean, so they are they're usually not very usual. Oh, that's a bad sentence structure right there. All right. So let me show you what I have here. So what I got is just this much. I didn't quite implement sibling of. So that one I did not implement. But the more complicated ones I did. Okay, so the first one would be just a whole bunch of facts because we have all the parenthood relationship between enough of the characters. So this way we can go up 5 generations and then go back down 5 generations. So this way Bart should end up as the fourth cousin of Violet. And I also put in Lola because Lola should be a fourth cousin of Bart, once removed. So we got all of those. All right. So yeah, that works too. I mean, you guys can definitely use fictional names and you use other ways of encode for people in the family tree. But this one is based on the Simpsons um, animated series. So right here we have ancestor and of. So ancestor and of is really the key to the whole thing. I gave you ancestor of from the class, but it didn't quite do the counting. So ancestor end of is basically the same thing. The end of the recursion is when you find parenthood. So when we have parent end of xyn, then we want to say if when n is 1, then x really should be the parent of y. So this really is the key to, I would say, 60% of this homework assignment, other than having to type a whole bunch of stuff to test it. So this is really the key is, when n is 1, then we are looking for x being the parent of y. And that's it. So for the other ones, I'm just looking at the text channel. Jonathan C. said the order of the statement does not matter in Prologue. It does because what Prologue does is it evaluates all of these in this particular order. So even though all of these are basically ors, it would evaluate from top to bottom. So if you reverse the order, you can potentially end up in an endless recursion. So it really should matter. Let's see. For example, your ancestor n of has n is n plus 1 as that last statement. Oh, okay. So you mean within the same clause? You mean right here within the same clause? So within the same clause, it depends. The way we have our code here, the only part that does matter is whether we check for parent of first versus whether we check for ancestor and of first. Because if I reverse the ordering between parent of and ancestor and of, it will still end up with endless recursion because ancestor and of would try to match the first rule, which will it would then fail, and then we'll go to the second rule, and then we'll recursively try to match the first rule again. So that would lead to an endless recursion. So that's why we need to have a parent of zy first, because that's a grounded type of predicate. It's either you can find one or you cannot, right? So if you cannot find one, it would just fail, and then it would just fail all the way back, and then eventually the whole thing would fail. So within a particular predicate, the ordering can be significant, but between these two, it may not be significant. Between n is m plus 1 versus xzm, that may not be significant, because it will find it either way. And we are not using the cut operator. And I'm not going to get into the cut operator in Prologue. Because the cut operator is an optimization technique. It basically says no backtracking beyond this point. So it's a way to say, okay, the solution you have gotten up to this point is good enough. Okay, don't try to give me 20 gazillion answers. I just need one answer. Okay, so don't try to backtrack and try to find me some additional answers. So we don't have a cut, and as a result, the ordering is not as important. Yes, it is the exclamation point in Prologue. You are correct, Jonathan C. All right, so once we have ancestor and of, common ancestry is really just saying, okay, can we find a person z so that z is the nth ancestor of x, and at the same time z is the mth ancestor of y, because that will basically satisfy the requirement that we have a common ancestor within n generations from x and m generations from y. But there's no need to basically say, but we cannot have any ancestor prior to nth from x and mth from y. Basically they can have common parents between x and y. They can even have common parents when n and m are both like 4 or 5. It doesn't really matter in this case. So the key to ancestry x, y, and m is we want the same kind of stuff as common ancestry, but there's one little thing. Okay, we do not want to have any common ancestry prior to nth generations from x and mth generations from y. So we want to exclude those things, and that's why we have ancestor and of, just like common ancestry. I could have just used common ancestry right here because it really is identical. And then in addition to that, I use two existential variables, existentially quantified variables, n1 and m1. So n1 is just n minus 1, and then m1 is m minus 1. So with these two, I can now specify, but not, okay, because backslash plus is the negation. It's basically saying, let's make sure that we cannot confirm this. So what we're trying to make sure that we cannot confirm is x, y, share a common ancestor within n1 generations from x and m1 generations from y. So that's the trick of excluding any earlier ancestors before we get to what we want as the common ancestor. So cousin is easy to define after this, because all we have to do is to confirm that n is greater than 1, because the closest cousin would be a first cousin, so n has to be greater than 1. R, which is the number of times removed, can be 0, but it cannot be negative. R has to be less than n. In other words, because if R equals to n, then you end up with y being a direct ancestor of x, which is not going to be a cousin. That would be a degenerated cousin, so to speak. So we want to enforce that R is less than n. And we want n1 to be n plus 1, because when we talk about first cousin, that means they share a common ancestor 2 generations ago. So that's why n1 is going to be n plus 1, because that's how we plug in to ancestry x, y, and m. And then m1 is n1 minus r, because r is the number of times removed. So that one, needs to be that amount should be subtracted from n1, so that we can figure out, how many generations the ancestor is supposed to be away from the perspective of y. So that is the quick summary. Obviously, I'm going to show it to you guys too, but let me go through all the text and see what is going on there. All right, so so there's no requirement, to implement it in this specific way. There was a discussion in the questions of, a common ancestry predicate should be used, but if it can be done without the use of a common ancestry thing, I suppose that's fine too. Can it be different? Well, it depends on what it is referring to. If it is referring to the functionality, then the answer is no. But if it is referring to the implementation, then the answer is potentially yes. Okay, I can show you all the pitfalls. Okay, all the things that um, this thing does not work. If you don't do it correctly. And then Jonathan R said R is less than N is something that messed me up because sometimes you can have first cousins once removed. Well, I don't know. If you have a first cousin once removed, don't you have an uncle and aunt? I mean, that's kind of a degenerated case of a cousin. Or I could be wrong. But can anyone confirm that, a first cousin once removed is basically an aunt or a cousin or an uncle? Okay, all right. All right, so and then Victor said, shouldn't then X and Y be the other way since it's R generations away from X? The child of a great uncle. The child of a great uncle. So I must be misunderstanding the number of times removed. So R is supposed to be added in that case to N1 and not subtracted from N1. In other words, you can have a first cousin twice removed if R is additive. Is that correct? I mean, so it is entirely possible that I totally misunderstood. All right, so let's take a look at the cousin chart. Thank you. All right, so here's you, same parent. We got sibling, same grandparent. Okay, let me move that window over so that you guys can see it too. There we go. And obviously it has to open it in a different browser than what I usually use, but that's okay. All right, so no, do not restore pages. There we go. All right, so let's take a look at this. So here's you, your first cousin, second cousin, third cousin. We got that. Oh, okay. So I got it. So okay. So this is my mistake, because I thought removed is going up in this way, but removed is actually going in the opposite direction like that. So that's totally my mistake. So if you guys implement it either way, I'll consider it correct. Yep, I totally messed up there because I thought removed is going up, and it turns out to be going down. Yeah, I suppose it can go both ways, but when people say once removed, it is going down this way. So, all right. So, any questions? I mean, other than the part about how many times removed, because it's just a question of are we adding R or are we subtracting R? That's the only difference. It's my interpretation was wrong. Okay, so when Armand is typing something, I'm going to get to a page because I thought that might be interesting too. So let me see if I can find that. Swish. There we go. Okay, anyone older, I don't know, is uncle, aunt. Anyone younger is kid. Uncle, I think in uncle and aunt, usually are one generations ahead of you or older than you. And they can be younger in terms of age, but in terms of generation, they have to be older, one generation ahead of you. Yeah, you might still get partial credit, depending on where you messed up. All right. I put r is greater than 0 instead of r is greater than or equal to 0. So you cannot have a just a regular fourth cousin. Oh, that's not going to be a big deal. I wouldn't worry too much about that, Jonathan. All right, so the one thing that I thought was kind of interesting that I want to show you is a combination of today is the last day of class, so I'm kind of free to talk about whatever I want to talk about as long as it still relates to the class, right? So I want to talk about this kind of this one Prologue script that is kind of interesting. But first of all, I want to make sure there are no questions about the one that was due today. So if you do have any questions about the one that's due today, let me know. And I'm gonna sign in to my account here because I got an interesting script for you guys to kind of take a look at. So, oh, it's going to ask me for the second factor authentication. Nope, did not save.
There's a lot of zeros in that account number. There's a lot of zeros in your ID number.
Yes, that ID is actually also my student ID, so the district does not differentiate between employee ID and student ID. So that just means that I started a long time ago. 21 years ago. There are some people with 4 digits of zeros, so they're way ahead of me too. But some people became students first, and then they became a staff, so it's not exactly. What is? Oh, okay, there we go. And screen share is gone. Okay, for some reason it crashed. I'm gonna restart it. There we go. Alrighty. Alright, so I want to show you guys this particular script here. It's something that I worked on just out of curiosity. So let me see, how do I get that back? Yep. Alright, so click on this. There we go. Alright, so this one is kind of interesting because it is it totally relates to this class because it is actually a combination between Prologue, which is predicate calculus, and graph theory. Now, in this class, when we say graph theory, it really is more about just the A-star algorithm and the Dijkstra's algorithm. Let me see what I'm missing in the text channel here. Will there be any Prologue questions in the final? The answer is no. I do not know yet. Yep. So I do not know yet. I'm still trying to figure out what kind of questions I want to ask for this semester. But I want to show you this. Okay, I want to show you this one because it's an interesting example of how various concepts of the same class, even though this class is really a potpourri of concepts. We have a little bit of this, a little bit of that, but I want to relate all the different concepts a little bit. Did the notes ever specify the concept of labeling functions? I'm not sure what you mean by that, Wade. You mean the predicates, not functions, like for find boundary being a quote-unquote function? It's kind of a function, but it's not entirely, a function. Oh, you mean function, like injection, surjection, that sort of function? I'm not sure. I'm not sure what Wade is referring to as functions. Okay. Well, we can talk about that when he gets back, and I just want to make sure that live stream is still on. Yep, it is. All right, so this is a representation of all the edges. It has a originating vertex, so V1 is an originating vertex, and then V5 is the destination vertex. So this is representing an edge, and then the number right after that is the distance of that specific edge. So I have a few functions here. Okay, so we'll go through these functions one by one to figure out what this Prologue program is really doing. The first one is boundary. It has x and h. So this is not a typo. X and h really just means we have both vertices being the same for the first two variables. So in this case, n is a number, and so is h. So boundary x and h is true only if h is greater than or equal to 0 and n is 0. So in this case, h is specifying the so the algorithm that I'm using here is called a successive deepening search for a shortest path. So it starts with just the starting point, and then it goes one level deep and see if we can find the solution. If not, it will you basically set a limit of how far it should go, and it will only go that many edges away from the originating vertex. So if the vertex we're trying to find a path to is the very same vertex that we are on right now, then we're done. Because in that case, it is 0 hops away. It's 0 edges away from where we are. So as long as the number of hops we are allowed to use is greater than or equal to 0, then we can consider that particular path found. So I hope everybody is understanding what this means. We are basically saying within n hops, okay, within h hops, can we find a path from a certain vertex to another vertex? That's what boundary is trying to say. So now we can give it a try. Oh, by the way, I forgot to test the other script, the cousins script. Do you guys want me to test it? Or am I... Oh, there we go. Sure. Okay, absolutely. I forgot about that totally. Okay, so you just have to keep in mind that my removed is actually opposite, or I can just change the script to fix that too. So I'll go ahead and fix that. So it's a plus. There we go. And yeah, so that will work. It will still work. And then I'm going to exit here. And to make this work, or to illustrate, how it works, it might be important to kind of go back to the Simpsons family tree. So because the removed is actually plus generation, it's actually adding more layers to the tree. So the way we can test this is we can take a look at Pomona, and I also have Lola. I also have Lola in the facts. So Lola is going to be a cousin of Bart because they share a common ancestor all the way up to Howland. The question is, what is the number of what is the I think they're fourth cousins once removed. Okay, so we'll check it out. Whether Lola is a fourth cousin of Bart one removed. Now, just from the family tree, we can work this out, right? So we'll work out and find out, at which point they share a common ancestor. The common ancestor, I'm pretty sure, is Howland. So Howland is, let's see, we are looking at Lola, and then this is 1 generation away, Furnace. This is 2 generations away, Twyla. And this is 3 generations away. This is 4 generations away. So it's 4 generations away from one side. So on the other side, so this is a third cousin. I misspoke. This is a third cousin, because on the other side is if we go down 4 levels, we only get to Homer. Because Homer's parent is one of the parents of Homer is Abe, and then we have Orville, and then we have Otut, and then we have Howland. So between Lola and Homer, they should be third cousins. So that's one thing we can check first, is to see if they are proper third cousins. So there we go. And the way I test it, because I have it installed, so I just have swipl, which is the name of the interpreter, and then we have cousins.pl as the script that you just looked at earlier. And now we can ask cousin. We first want to confirm that Homer and Lola are third cousins. 0 times removed. And press the enter key. And it says it's true. Now, the interesting other thing we can do is to check, what is the how they rank as cousins. I have never tried this. Okay, I don't know whether this is going to work or not, whether it can identify they are third cousins or not. And the answer is no. It doesn't quite do that. Having the number as a variable is harder. However, I can do this. Okay, this I know for sure I can do. In other words, find me all the third cousins of Homer, and it will find Pomona and also Lola. So that's kind of cool, because now you can say, I want to find all the cousins of this many generations ago and this number of this many times removed. All right, so let's go the opposite way. So this time we want to say Pomona here, or Lola, and we want to find third cousins one removed. Okay, and we should be able to find the entire all the kids of Homer should meet this requirement. Before I go any further, let me just kind of give you guys a little bit of time to ask questions if you have any questions. Any questions? Nope. Okay. All right. Well, we'll give it a try. So we find Bart, we find Lisa, we find Maggie, and so it does find all the third cousins once removed. Now that I fixed the number of times removed, adding instead of subtracting it. So that was totally my own misunderstanding that it's supposed to be subtracted. Which also means the check to make sure that r is less than n should not be there either, because it doesn't make sense. All right, so I thought one of the Jonathans was typing, so I'm gonna wait a little bit here. And while we're waiting, we can also test out some of the other cousinships. So we can ask who are the second cousins? Second cousins of Lola. And in this particular chart, we do not have any. We only have the third cousins, and that's because Howland was the first, or it's the common ancestor all the way up. All right. So Wade has a question.
I do, yes.
Yeah, go ahead.
Okay, if we were gonna do a simulation like for a video game, like a simulator.
Yep.
And we wanted to keep track of a community's kinship, right? So the relationships people have. Would Prologue be a good language to implement that in? I know it's kind of used for AI, but I think that's more like neural nets and stuff.
Well, there are different kinds of AI. So Prologue addresses one very specific aspect of of AI, and that's basically reasoning. Because neural nets, as far as I know, cannot do symbolic type of reasoning. And then Prologue is the entire purpose of Prologue to exist is the implementation of predicate calculus. And predicate calculus is invented, or it's basically used for reasoning. It's the souped up version of propositional logic. So if your game involves having to figure out the relationships between the in-game characters, and you can define those relationships as you said using kinship, then Prologue is a possible way to try to figure out all the kinship, the relationships. But it doesn't have to be Prologue, because whatever Prologue can do, you can basically write it in C or C++. You can use a very very rigid and very kind of low level type of high level a low level high level programming language. Yes, that's what I just said, because C and C++ are considered very low level compared to Java and some of the other high level programming languages.
Yeah, I have I think I'll have an associate's in the C++ programming, I think after this semester.
Hmm.
I love C++. Yeah, it's very, you can get really nitty gritty with it. That's what I like about the language.
Yeah, but you can also have all kinds of bugs. So if you
Yeah.
yeah, if you corrupt the stack, in other programming languages you can still have all kinds of bugs, but corrupting the stack or corrupting the heap is not one of the things you can do with most scripting languages, and Java is the same way. You cannot really corrupt the stack. But in C and C++, it's so easy to corrupt the stack, which is not um, corrupting the stack doesn't sound like a very bad problem, but it is really bad because you can mess up the saved information on the stack, which means it can return to the wrong place. It can also mess up what we call the base pointer, which is also called the frame pointer. And if that thing is messed up, then when you return from a subroutine, the caller is gonna have everything being offset by. That's one of the worst thing that can happen. Is all your variables got shifted. So if you originally have variables x, y, z, okay, then you will see that y becomes x and then z becomes y. It's like, what just happened, right? Uh, and there are certain bugs in C and C++ that can lead to a symptom like that. You can also have a symptom of you're returning, but you're returning to a function that you never call, that was completely inert. It was just sitting around in the program. Nobody called it. And yet, after you return to that function. It's like, how did I get here? That's because the return address got messed up, but it's not messed up in a major way. It just got messed up in a minor way. So you just adjusted where you land when you return from a subroutine. So instead of landing where it's supposed to, it just lands at a neighboring function, and then all kinds of bad things happens because execution actually continues. So you may not even see a symptom. The program even may not crash for a long, long time. By the time it does crash, it is so far away from the actual reason why the fault is it's already long gone. You're just looking at the aftermath of the whole thing. So anyway, that's just me yakking around to basically explain why C and C++ are considered pretty low level when it comes to high level programming languages. But the original question was whether it is embeddable or not. Okay, so let me try to answer that question because today is kind of our last day and I don't really have a set plan other than talking about doing shortest path, length of shortest path search without using Prologue. So anyway, let's get back to that question first. Okay, so my screen is kind of small right now, so I can't really see a whole lot of stuff. Yeah, just don't make errors. Well, I have not seen a program that is worth writing that has no bug. Yes, sure, you can certainly write programs without bugs, just not one that is worth writing to begin with. Yeah, exactly. Yep, exactly. Hello world. Always worth it. Yes, but okay, it depends. If your objective is to make sure that your tool chain is working correctly, then yes, Hello World is great. Okay, it makes sure that your compiler is working, it makes sure that linker is working, and it does check a whole bunch of stuff. Okay, all right. So to address Wade's question, whether it's embeddable or not, it depends on what platform you're using. So if you look up SWI Prologue, SWI Prologue architecture, it's probably cross-compiled to many, many different architectures. And I don't think this is the architecture as in computer architecture. So I'm going to search for this in a slightly different way. I'm going to look for SWI Prologue Debian, because Debian is a distribution of Linux, and when we go to a specific package, it will tell us, how many platforms it has been ported to. So you can see right here that it has been ported to basically all known platforms in Debian. I can explain a little bit of this. I know most of you are not interested, but I will still go ahead and explain a little bit of this. AMD 64 is applicable to most PCs and also Macs. ARM 64 is applicable to, I think, Raspberry Pi are now 64-bit wide, so I'm suspecting ARM 64 does apply to Raspberry Pis too. And then we have i386, which is your usual, the older PCs running in 32-bit mode. MIPS are interesting. The MIPS processor are a UC Berkeley kind of processor. They originally used it to teach computer architecture. It's a very kind of it's a weird little architecture for sure. So, but it's not very widely used today anymore. PowerPC, PPC is PowerPC, 64-bit, and then we have S360, System 390. Okay, that's an IBM mainframe processor. So it has been ported to all of these different platforms, but because it's an open source product, all you really need is to cross-compile it to whatever platform you want to run it. So from that perspective, it is kind of embeddable. You might even find it in Windows. So if you just look up SWI Prologue Windows, pretty sure it's available. I mean, it would not be difficult to do that. So it has a 64-bit, 32-bit version for Windows, and it also has one for Mac OS X. I mean, the Linux side is super easy. For something like this, it's the other platforms that's kind of questionable. So there you go. So if your game environment can shell out, so to speak, to run a script, outside of the game engine itself, and then just collect the answer, from the external script, then you can certainly use Prologue, for certain things. So I hope that kind of answers your question. Not wait. Alright, so here we have a few other things in the text channel. I meant more embeddable like Lua is, where it's run within an interpreter. Yeah, Prologue is always running within an interpreter itself. What are the possible topics? Armand is trying to keep us on topic here. What are the possible topics for the exam? So everything after exam 2 is in scope. So predicate calculus is in scope, graph theory is in scope, probability event counting is in scope. The big O and the recursion thing, I promise you I won't be asking questions about big O and recursion stuff. Propositional logic is already done in the past, so I'm not going to have specific questions for propositional logic. Relations, I won't have any specific questions for that either. But functions is okay. So we use functions, right? In both of the algorithms, in the graph, in Dijkstra's algorithm, and also A-star algorithm, we actually made use of the concept of sets and also functions. So I cannot say that we are not going to have questions that require the understanding of functions, but I will not have a specific question for functions. Yep, so it's not exactly comprehensive. It does rely on some of the earlier concepts that we have already introduced. In other words, if somebody is to say, so Tech, we don't need to understand unions anymore, right? And I go like, no, because the algorithms that we have talked about, like Dijkstra's algorithm and also the A-star algorithm, they both refer to set operations like unions, check for existence in a set, and so on and so forth. So there you go. Is there any way we could have a practice cumulative test? No. I don't have one available, unfortunately. Alright, so I think Armand says, I'm gonna focus hard on graph, probability, and Prologue. Yep, I think that would be wise. That would be wise, and in that specific order too. I would okay, graph is definitely going to be there. Okay, so between the A-star algorithm and the Dijkstra's algorithm, there's going to be at least one question for that. Okay, so you're guaranteed. That part is guaranteed. Probability, is also guaranteed. Okay, so you got to understand what is a binomial distribution, and also what is the other one? The counting, the lotto problem, and also the non, the one where you have more than 2 outcomes per trial and it is with replacement. So that's the easiest one. We talked about that one when we talked about the birthday problem. So when we talked about the birthday problem, omega, or the cardinality of omega, is 365 to the power of number of people in the class, right? Or the number of people that we're concerned about, and that's because everybody can choose one of the 365 days in a year, and that will basically be the omega, because that is the set of all the possible outcomes. What we are interested in when we talked about the birthday problem is the case when everybody has a unique birthday. So that is when we say, okay, here's the set of the event, right? The event set. The event set is basically the set containing all the outcomes that are of interest to us. But in that case, the cardinality of the omega is 365 to the number of people in class, which basically means each trial, which is basically each person, has 365 possible outcomes, and it is with replacement. Just because somebody is born on a certain day doesn't mean the next person cannot be born on the same day. All right. So in terms of probability, you basically just have 3 varieties, right? So I'm going to help you guys out a little bit here, and let me spell out the 3 different types. We talked about this a little bit last time too. Yeah, so with the prologue thing, I was just about to show you what I have here. So maybe we can just kind of quickly go through this, maybe. Okay. All right. So so I'm gonna give you. Okay. So I'm assuming this is okay. I'm gonna give you a test run of boundary. So boundary is trying to see if there is a connectivity between 2 vertices within a fixed number of hops. So I don't have a graphical representation of this, but I think if you guys just kind of quickly go through so V0 and V4 are connected. Okay, so we're gonna say V0, V4, and I believe they are connected within 3 hops. Okay, so let's double check. So V0 goes to V5, V5 goes to, let me see. Okay, so we want to get to V4, so V3 is here, and V0 goes to V3, V3 goes to V4, so it's within 2 hops. So that means, H can be anything greater than or equal to 2, so 3 would work also here. And then we just, kind of leave this one empty and give it a X over here. And then we press Control Enter, and it finds the shortest path, between V0 and V4 is 6. Okay. You can also reduce the number of hops. Okay, so if you reduce the number of hops to 2, it should still give you. Oh, okay, I guess not. So if you reduce the number of hops to 2, it does not give you. It says false. Let me just double check. There we go. Yep. All right. Well, this is the problem of me not leaving behind any comments. But let's read the code and see what it is trying to do here. All right, so this is the base case. The base case is, oh, I see why it's a problem, because 2 is not, we are running out of edge hops here when we specify 2, because, okay, because the base case is when we are on that vertex itself. Okay, so when we are on that vertex itself, n is going to be 0, which means it doesn't cost us anything from a vertex to go from a vertex to itself, and then the number of hops just has to be greater than or equal to 0 to basically means that, yeah, we still have, we still have room, for that particular exploration. So what if this is not true? What if we cannot, what if x and x are not the same? Like in this case, v0 and v4 are not the same. Then we go for the second rule. The second rule first make sure that we have at least one hop left. Okay, so this is, oh, so that's why it's having a problem, because this is supposed to be x is greater than or equal to 1, not just greater than. There we go. So let me fix that right away. So this part here is just making sure that we have some remaining number of hops. So we're not quite there yet, but we think we might be able to do it. So we have to make sure that we have enough hops left behind. So that means so h1 here is h minus 1. So it's reduced by 1 if I can find an edge z, xz. So now I'm looking for a path from z to y, but then the number of hops I have left is h minus 1, and h1 is h minus 1. So that's why when we look at this h1 here, it is 1 less than what we are given with, because we just used it up on one single edge over here. And then n is the cost. Okay, so n is basically the length of the path itself. So it is n1 plus n2, because n1 is the distance of the edge from x to z, and then n2 is the length of the path from z to y. So z itself here is an existentially quantified element, which basically means I just need to find a z such that xz is an edge, and then z to y there's a path, and then the edge itself has a distance of n1, and then the length of the path from z to y is n2. So if all of these requirements are satisfied, then I can claim that n is n1 plus n2, because now I have found a path from x to y through z, and it has and the length is going to be the distance of the edge plus the length of the path from z to y. All right, so I'm gonna check the text channel. Yeah, so hop is the number of edges. Yep, exactly. So Aman is correct. Hop is like the number of edges needed to go from one vertex to another vertex. Function graphs. Yeah, a picture would help, but I don't have one. I suppose we can make one right away on the fly. Oh, by the way, if you use Joplin, okay, let me get this started here, because today is kind of a looser day, so I'm not exactly too concerned about getting things on time. So I need to go to Joplin. I'm using a different account on the same computer, because the screen size is different, so I don't want to mess up the placement of my windows of my other account, and that's why sometimes to get something working, I have to go through a lot of hops to do it. All right, so now we have Joplin, and this is CISP440, and I can make a new note here. There we go, 2021 1208. That's today. All right, so one thing that's kind of cool about Joplin is you can actually use Joplin to make graphs. Now I'm putting this here, not only because I want to kind of give you guys an idea of how to make graphs using Joplin, but you can also use it, in the exam. If you want to visualize the graph, this is potentially one way to do it. If one of us makes one, yeah, you guys can image it, sure. But I'm a little obsessed now with using Joplin or Markdown. It's called Mermaid. The language is called Mermaid, and you can use it to make a graph using a Markdown kind of language. It is not as difficult as one would imagine, and what we want is kind of a flowchart, so I'm just going to go to a flowchart here. Alright, So we want a flowchart LR, which is left to right. And okay, so arrows are indicated by that. And I think these have all be inside a mermaid block of code. So let's give that a try. Okay. So we have mermaid. There we go. Okay. That's a good sign. And we want a flowchart LR. And okay, let's just try A to B. There we go. That works. Kind of cool. All right, so now we can switch back to SWI Prologue, not this one, but the swoosh. There we go. All right, so we got V0, V5 having a cost of 3. So let's give that a try. V0, 3 to V 5. There we go. Okay, excellent. All right, so if that works, I'm gonna do something here to make my job easier. This is going to be a Prologue block, and I'm just gonna copy and paste the Prologue configuration here. So yeah, unfortunately, I'm not so good with scripting where I can just instantly come up with a script and translate all these edges into Mermaid, like just like that. So I'm not quite that good with scripting. Alright, so we got that. Next one is V0, 3 again to V1. And then we have V1, V4, 2, V1, 2, V4. And then V3, V0 cost with 2, 2. Is it with V3? Yep. And then we have V3, 1, V4, V0, 1, V2, and then the last one is V2, 1, V0. Yep. There you go. Alright, so I'm just trying to catch up with all the text traffic again. If one is okay, we got that. How soon will we know the result from our final exam and all the homeworks? Yes, I've been falling behind a little bit in terms of grading. You would need to do Vim recording, right, in order to automate it. I was more thinking about just copy and pasting the text into the input, the standard in of a program, and it will just do all the. I mean, Vim can do this too, because all this is to rearrange things a little bit. So with regular expression, it actually can be done. I'm just not that good with regular expression in Vim to convert the representation of edges in Prologue into the mermaid representation. But it's totally doable. It's just that I'm not that good. So that's my answer to Wade Jonathan Camarena. So there you go. Yes, I am using Vim in Joplin, but I don't think regular expression works that well in Joplin. I mean, we can give it a try. So V \D. Oh, it does work. Okay, cool. Oh, okay. Something doesn't. I think. Nope. Why is that not working? Oh, the greater than. There we go. Okay, so it does work. Nice. Thank you. Wow. Okay, I am kinda impressed. All right. Cool. Oh, by the way, the error message kind of suggests, what programming language Joplin is written in. Let me do that one more time. So there we go. JavaScript regular expression. So I'm suspecting it is written in JavaScript. Doesn't have to be, okay? It just has to be consistent. But just my suspicion. Anyway, so this is the graph, and we are trying to look for the shortest path. Okay, that particular program looks for the shortest path. I like JavaScript. It can be a little bit it can be a little bit difficult when it comes down to debugging the program, and sometimes I have really poor programming style. All right, so if we want to find a shortest path from V0 to V4, just from eyeballing the whole thing, you guys can see, oh, okay, this is the shortest one. We go from V0 to V3, and then we end up at V4. So the shortest path, has a length of 3. So now we want to look at the other predicates. So boundary is just that. Okay, boundary is basically just saying if I need to go from one vertex to another vertex, and I limit myself to the number of hops, what is the best? It doesn't necessarily find the best path. It just finds a path. So what does RIP sign means in Swish? I'm not sure. Oh, this tombstone. It means I think it means it has exhausted. All the it ran out of time, maybe. All right. So next. Okay. So it's a timeout. Jonathan, it's a timeout because SWI because Swish is running on somebody's server. So if I don't click a spacebar to look at the next possible answer, it's gonna consume memory to maintain the state of this particular query, waiting for me to press the spacebar. And I guess a lot of people don't care to press the spacebar, so it has to time out so that it can basically stop this query and reclaim the memory. That's what the tombstone is about. It's just timing out. All right, so we can now see that the boundary is interesting because not only can it find the length of one path, it will basically find the length of all the paths from a certain vertex V0 in this case to V4. So now the question is, how do I find the shortest path? So this is where it's kind of interesting because now we basically say we're trying to set a boundary and say we are only interested in paths within a certain boundary. So there are two constraints. One constraint is the number of hops, which is basically translating to the number of edges that we're supposed to traverse from one vertex to another vertex. But the second boundary is in terms of the length of the path. So we are only interested in paths that have a length of less than or equal to a certain additional constraint. So that is the interesting part of this particular algorithm. So boundary is easy. Boundary is basically just going through all the possible paths within each hops. And it will tell you, the length of every single one if you leave n unspecified. Okay, so wait, why is number of hops a constraint? Because we basically want to start low. We want to start with like a very low number, and then we bump it up until we find out, okay, how many hops do we need to get to the destination. So I can explain that in just a little bit. You could have like 4 hops within each edge being 0 minus 1. Yeah, so if you increase the number of hops, it would actually find more paths. Okay, so let me show you this. So let's bump it up to 4. Okay, and it will say 6, 5, 3, 8, 7, 5, and that's it. So you guys are now thinking, why? How can we find a path of 8 edges in order to go from V0 to V4? Let's go back to the representation here. So, so the way it works is it basically goes through this loop here. So this loop, each time you go through this loop, it's taking up 2 edges, right? 2 hops, and then it will just add those 2 to this 3 being a 5, add 2 to 5 being 7, and then add 2 to 6 being 8. So that is the reason why we end up with these 3 additional values, is because oh, so you're giving me all of these different hops, let me use up all the hops, right? That's what the algorithm is doing. It's using all of the hops. It doesn't have any loop detection whatsoever. Yep. It's just saying, let me use up all the hops, in order to get to the destination, and I'll give you the length of not the path anymore, because now it is a walk. Remember, in a path you are not going to repeat a vertex, but in a walk there's no there are no restrictions. So this is basically a walk and not a path anymore. All right. So boundary is pretty simple. You're basically just saying, I'm going to tell you where I want to start. I want to tell you where I'm going to stop. I am going to give you the total number of hops that you can use, and you just have to tell me what is the length of a path from the start vertex x to the end vertex y that is going to use up all the hops. Potentially using all the hops, because as you can see, the 6, 5, and 3 do not use up all the hops. They just use up like 2 of the hops. So there we go. Okay, so now we have find boundary, as a separate predicate. It makes use of boundary. So what does it do? Okay, so that's the first question. So the first definition of find boundary doesn't tell you much. It just says find boundary will just return boundary itself, using exactly the same parameters. Okay, x, y, n, and h. But then we look at find boundary, the second one. The second one is a little bit different because it has it makes h1 h plus 1, and then it calls find boundary again. So this is the one where we say, okay, let's start with a low number of hops. If we cannot find anything, if we cannot find a path between vertex x and vertex y, just having 1 hop, let's bump it up to 2. If we still cannot find something, let's bump it up to 3, and so on. So in this case, it would actually find the number of hops to get from vertex x to vertex y. Exactly, since it always increments. So let's give it a try. Okay, so we're gonna try find boundary, and we're gonna go from v0, v4 again, and this time n is always unbound because we want to. Because n basically becomes the length of the of a path, and then we'll give 0. Okay, we'll have 0 as our number of hops, and we'll see what happens here. Control Enter, and it says 6, and it's going to go through all of the same thing, except this one does not stop. It just keeps going and going and going, because it goes back to this case here. When I exhaust all the cases up here, it just kind of goes back here and then increase the number of hop by 1, and then it will go again and again and again. All right. Now I think I can make this also a variable. So let's make h also a variable here. And it doesn't like it. Okay. So I guess it doesn't work that way. So we cannot find the number of hops. We have to specify we start with 0, and it will keep going, and finding, it will bump it up until we get to a path between vertex x and vertex y, in this case from v0 to v4. Alright, so next predicate is path bound. So let's check out what path bound is trying to specify. It has x, y, n, and l. And the first thing is, so instead of looking at this as a program, you can look at it as a predicate, because that's the whole idea of Prologue, is everything is a predicate. So this predicate says path bound x, y, and l only if, okay, so we need all of these three to be true in order for path bound to be true. So we need to have an edge going from x to y with a distance of d. We need that d to be less than l. So l is a limit, okay? So you can consider l as a limit of what is the length? What is the um, what is the limit of the length that we would still be considering as okay? Okay, so d has to be less than l, which is a length type of constraint, and then n is d. N is this one here, so that is the distance itself. So in this case, whatever this d is instantiated, it will also bind to the value of n. L obviously has to be given first, okay, so we have to be given L, and that's path bound. In other words, it is asking, can we find a path from x to y where the length is bound by L as a parameter? And then n is returning the actual length of the path. Let me say that one more time. Path bound in the base case is asking, is there a path, in this case just an edge, but an edge is a deformed path, is there a path between x and y where the length of the path is less than the constraint of L, and use n to return the value of the length of the actual path. So you're now setting an upper limit, an upper bound, so to speak, of what the length can be, but then we also want to know exactly what the length is between x and y. And the base case is x and y are connected by an edge. So what if this fails? What if x and y are not connected by an edge, but they are reachable using a path? Then we get to the second one. We get to the second path bound. Oh, okay. Well, this is why I use Mermaid, because I will let Mermaid to kind of optimize, all the paths. I can post this into the text channel. I mean, if that is what you guys want to do. Let me do a screenshot. There you go. This is why I like Discord so much more than Zoom, because I can't do this with Zoom. Well, not easily. I mean, I can post a link in Zoom and you guys can follow the link and open it up. Alright, so getting back to the Prologue program. So the second definition of path bound is the recursive one. So the recursive one is saying, okay, let's make sure that we still have a constraint left, okay? Because when L becomes negative, that means, sorry, we have just used up, all the length that we're given with. So, we basically just have to declare failure in that case and say that, no, I'm sorry, we cannot do this anymore. So as long as L is greater than or equal to 0, we are looking for an edge between x and z. So you can see how z is not a part of the left-hand side of the predicate. So z is an existentially quantified variable. It basically means there exists, okay, an edge xz with a distance of n1, and now we want to specify it's n1, but we want to specify L1 as L minus n1, because that's the new constraint, because we have just used up n1 amount from the constraint that we were given with as a total. So the leftover amount is L minus n1. I can still see your original names, and I still recognize Discord name of certain people, so I can still kind of distinguish who is who.
Is it clear that my picture is like a very strange looking cat?
Your picture?
Yeah,
Oh,
is that clear?
the picture part is yes. So I can see you are a gray cat. Is that Tom and Jerry?
It's like a very weird wild species of squashed cat. It's yeah.
Okay. Yeah, that's I can see that in the voice channel. In the text channel I cannot see any avatars. Alrighty. Alright, so getting back to here, L1 is the new constraint because we have just used up N1 amount from my original constraint of L. So now I call path bound again and say, okay, we only have L1 left, okay, as our constraint. And then N2 is an unbound variable at this point because I want to find out, can I find a path between z and y within the constraint of L1? If so, I want to know what the length is, and N2 is the length of a path from z to y, and then the total length of the path from x to y in this case is just going to be n1 plus n2 because n1 is the distance of the edge from x to z, and then n2 is the length of the path from z to y, and by the time I get here that means it is already found. So path found is using a given a specific limit, okay, as a constraint, it will try to find a path between two vertices and then it will return back with the actual number. It will return back with the actual length of that path. So let's go ahead and give it a try. So we'll go ahead and try out path bound, and we'll give it something that is impossible. Okay, so v0 to v4. N is unbound because it returns the actual length of the path, and it will specify something that it cannot accomplish. Okay, so if we use 2, it's not possible. There's no such thing as a shortest path between v0 and v4 where the length is less than 2. So when we try to ask that question, it just says nope, we cannot make it happen. Even 3 cannot happen because of the comparison is the comparison is greater than or equal to 0. So 3 maybe should be doable. Nope. Oh, why is it not doable? Okay, let's try the more obvious one. Okay, so it finds 5. It also finds 3. And then, okay. So there we go. Huh. But it's not. Oh, right, because of this comparison here. Okay, now I get it. Because this has to be less than that. So L is an upper bound, but it's also a you cannot touch L. Okay, the actual length cannot be L. It has to be less than L. So that's why 3 doesn't work. 4 should work. 3.1 should work. Right. So, yep, that works. Okay, now we got it. All right. So now we got some somewhat interesting predicates. And now we want to look at your shortest path, because that's the last one. It's like we are building tools to get to the shortest path, to find the length of the shortest path. It doesn't actually return the path itself, unfortunately, because to do that we have to utilize the concept called a list in Prologue. So yes, Prologue actually has a built-in type called a list, and it has ways to extract the first element out of a head. It has a way to extract the head, which is the first element, out of a list, and then use it for recursive purposes, because that's the whole idea. With any type of list, if you take away the first item of a list that is non-empty, the rest of the list, guess what, is also a list. So that's kind of how Prologue can make use of a list. It can either break apart a list and confirm a particular thing, or it can also construct a list along the way when it is trying to find a solution. But I'm not using a list, so there's no way I can actually print a path. But what we're interested in, how the one predicate left in this program is shortest path. So shortest path is just x, y, n, and the first thing it does is to do a find boundary. So, and in that case, it is using a 0. So it's basically saying, give me the length of a path, okay, between the two vertices. And let's try with 0 edges first. And if 0 edges doesn't work, bump it up to 1. If 1 doesn't work, bump it up to 2, because that is what boundary does. Okay, if you go back to find boundary, it says, if we cannot find, something within that within this number of hops, let's bump up the number of hops and try again. That's basically what find boundary does. So by the time we have satisfied the first predicate, we would have found the length of a path between the two vertices, but not necessarily the shortest one, right? Because we just go like, yeah, I'll just give you one of the paths. So in the case of the graph that we are working with, it is entirely possible that we'll find the path with the length of 6. So it's going to use the path of v0 to v5, and then from v5 to v4, which is not optimal. It's not the shortest path, but it will return a bound. And then the second predicate here is a negation of path bound x, y, and then I use an underscore here, which means it is unbound, but I don't even need it back. Okay, so what does that mean, right? What does the second or line 39 mean in this case? It's basically asking, can I find a shorter path? So if find boundary is returning true and it's giving me a specific value for this n, all it's saying is, yeah, I found a path between the two vertices and the length is this. That's all it's confirming. So what the second line, or line 39, is trying to say is, but if this is not, if I can find a shorter path, I want to send you back to find me the length of another path. That's what it's doing. Okay, it's basically saying, if this is true, that means a shorter path exists. And because this is a negation, it means, sorry guys, as a whole thing, line 39 is false if there is a shorter path. Then it goes back to the first line and goes like, oh, okay, let me get another path. And then we'll go back here and say, what about this? Okay, it will go back to this line here, and it will ask, what about this path? Can we find a shorter path? Oh, yeah, we can find a shorter path. Let's go back to the first line again. Let's find another path. Okay, give me the length of another path. So it's doing this until this predicate here, including the negation, is true. Okay, because if this entire thing is true, that means I cannot find a shorter path anymore. So if you cannot find a shorter path, that means the length of the path that you just found was indeed the shortest. So that is when it gets to the first line, the third line, and we briefly talked about this at the beginning of today's lecture. This is the cut operator. So the cut operator has a value of true, but it also serves a very strange purpose of, we're done. Let's not backtrack anymore. We are done. Okay, so that is kind of the whole the mechanism of this particular algorithm. So we'll go ahead and see whether this works or not, right? So we say shortest path, v0, v4, and then n is unbound because I want to know the length of the shortest path. So we press Control Enter, and it found the shortest path is 3, and it's definite. It doesn't give me an option and go like, do you want to explore any more? Nope. Because of the cut operator, it doesn't backtrack anymore. Alright, so let me read the text channel. Like the O in the A star where you're looking for something shorter. It's actually not like that. It's more like, I just found the length of a path, and then it's trying to confirm, can we find a shorter path? If we can find a shorter path, then we have to go back because the \+ is a negation. And then the next text message is there a debugger like GDB but for Prologue? Yes. So Prologue does have a debugging capability. I'm not sure whether the user interface here has one or not. Doesn't look like it, but it does allow you to single step and trace through the evaluation of the predicates. So if you look up SWI space Prologue space debug, you will probably find the command line stuff that you can do within the SWIPL interactive environment for debugging. And then Armand said, can you quickly go over the basic probability types so we can expect as mentioned earlier? Yes. Okay, so let's go back there. So I hope some of you find this Prologue program a little bit interesting. I can post it just in case anyone is interested. This is also why I like Discord a whole lot more than Zoom. Is I can just copy and paste a program, and as long as I specify the correct language, it's syntax highlighted correctly. It's very good for people lazy like myself. Right. Okay. So we are going back to the discussion of the probability stuff. All right. So let's talk about probabilities. So types, okay, of probabilities. Okay, there we go. So we're going to talk about the first one, the one that is the kind of the odd person out, okay, so we're going to talk about binomial distribution first. All right, so there are certain constraints, okay, so constraints is really a good way of thinking about something, because it is basically saying, okay, in order to be considered, all of these conditions must be met first. So now we're going to talk about all the constraints. So the constraint of the binomial distribution is each trial has two outcomes. So that means, when you look at each trial and it has 365 outcomes, then you're pretty sure that you're not dealing with a binomial distribution, because, in binomial distribution, each trial can only have two outcomes. With replacement, which means, every single trial has two outcomes, okay? It's not like, if you flip a coin, the first one lands on the head, and, the second flip cannot land on the head anymore. That doesn't make sense, right? When you're flipping a coin, each one is independent, and every single trial has exactly the same two outcomes. So that is the second constraint of, when you think you are dealing with a binomial distribution. But then one of the unique features of binomial distribution is the probability of each outcome for each trial may not be exactly the same. Okay, so the probability of each trial outcome does not need to be the same. So does not need to be 0.5. So that's one of the very unique things about binomial distribution, is you can be lopsided. You can think of if you think about the coin flip, it's usually kind of close to like 50-50. Even with a loaded coin, it's not going to be that obvious, like 0.999 versus 0.0001. On the other hand, if you look at the transmission of a single bit, okay, using whatever transmission mechanism you want to use, then it is very lopsided, because most of the time, okay, 99.99% of the time or more, it is going to be transmitted correctly. There's a very slight chance that it does not get transmitted correctly. So that would be the other extreme of a binomial distribution, is, most of the time it is close to 1, and very, very occasionally it will get the error bit. Okay, so that's the nature of binomial distribution. So I think binomial distribution kind of stands out because because of the two outcome thing, and also because of the probability of each outcome doesn't have to be even within those two outcomes. So the second one is going to be, I was just put quotes here, without replacement. Okay. And this is a broader category because there are two subcategories. So when we look at this, we have certain constraints again. Okay, so constraints. There we go. So the first constraint is the outcome of a trial is not available for further trials in an experiment. That is the first and most important constraint, that will say, that is going to scream and say, this is one specific category of ways to compute probabilities. Now, to be fair, this is not computing probability. This is about counting, okay? So let me just kind of make that clear at this point here, okay? This is about counting. Now, counting does relate to probability, but only if you have something to divide it by, okay? So until you know what to divide it by, then it is not a probability. It is just it's just a count, okay? How many ways can we blah blah blah, okay? All right. So within without replacement, now we have two things that we have to distinguish. Okay, let me take a look at the text channel. Is binomial the only one with replacement? Nope, it is not. So we're going to get to the with replacement next. Future trials or further. So it is the outcome of a trial is not available for further trials. So that means that once you have chosen something out of a bag, you do not put it back into the bag. But then it has two subcases. Okay, so subcases. So one subcase is when ordering is important, and then the second one is when ordering is not important. So when ordering is important, we are dealing with permutations. When ordering is not important, we're dealing with combinations. Now, when is permutation important and when is when is ordering important and when is ordering not important? That is a little bit harder to qualify. For example, okay, in the case of the birthday problem, okay, there's no inherent ordering, right? But ordering is important because who gets which date, is important. So let's just okay. So this is another trick. Okay, I'm not gonna write it down, but you can kind of jot down the notes here. So when you want to resolve and ask, okay, which one is this? One trick is to reduce the problem size to one that is almost trivial. Not trivial, but almost. Because if I just say, okay, let's think about the class of one person, it doesn't really help because, whether there's ordering or not ordering, there's only one person. You cannot distinguish, okay? But when you have a class of only two people, then you can ask, okay, so if I want to count the number of ways where the first person and the second person do not have the same birth date, okay? Would I count the first person having New Year's Day and then the second person having the last year of the day as one case, and then the first person having the last year of the entire year, and then the second person having New Year's Day? Would that be considered two distinct cases? And the answer is yes. It should be considered as two distinct cases. So that means ordering is important in that case, okay? Because who gets which date is important. We are not only saying, oh, one of these people have this date and one of these two people have that date. No, we need to know who has which date because it makes for two different scenarios. Yep. So that aspect, okay, whether ordering is important or not, is a little bit harder to answer. I can't really give you a canned statement where if you answer this statement, you will know whether ordering is important or not, because ordering sometimes does not look like ordering. It just says, it's just different. Now, when you look at a lotto problem, ordering is not important, okay? Because when you look at the numbers, in a lotto, and let's just say that you bought a ticket, okay? You bought a lotto ticket, and you were watching, when they, when they were drawing those numbers out of the basket, okay? It doesn't matter, whether okay, let's just say that your ticket has 1, 2, 3, 4, 5, and we don't care about the Powerball, okay? So let's just say your ticket has 1, 2, 3, 4, 5, as the numbers on your ticket. So when you're watching how they drew those numbers, from the basket, okay, whether they drew those numbers, in the order of 5, 4, 3, 2, 1, 3, 4, 5, 1, 2, or 1, 5, 2, 3, 4, it doesn't matter, right? You're still gonna get your share of, you're still winning, right? And I think it's up to what, 200 something million dollars now, because nobody won the jackpot for a long time. Anyway, so ordering is not important when we are talking about the lottos, okay, the lottery thing. So the vacation thing that I used as an example, I'm not sure. Did I use a vacation as an example somewhere? I think I did, right? Yeah, that's our homework assignment, I believe. No, that's not. I thought that we talked about an example where two people were picking destinations, right? Yeah, we had Lotto as a homework, but I did talk about the vacation spot problem. Yeah, the travel example. It wasn't a homework thing. What was it? I know better. I'm not going to buy any Lotto tickets. Even though the possibility does exist, it is slim enough that I don't really care about. Yeah, so anyway, I believe we did talk about an example where two people were picking destinations out of a travel brochure, and they can only get to go if they overlap and chose the same destinations. I think we talked about that. So in that case, okay, ordering may be important, it may not be important. Okay, it's up to the question to state clearly whether the sequence of going to Hawaii, Alaska, and finally Yellowstone National Park is important or not. Okay, so do they have to specify everything in the same order or not? Okay, so that is part of the question to specify. So it's harder to distinguish between the cases where ordering is important versus when ordering is not important. So that one you just kind of have to read the question to figure it out. All right, so the last one is with replacement, and these are the really simple ones. Okay, the birthday problem is the best illustration. So this is the omega of the birthday problem. In other words, the omega of the birthday problem is asking how many ways can we arrange birth dates, okay, given n people in the class. So once again, you want to reduce the problem size to a small number, but not a trivial number, okay? Because if you reduce the entire class to just one person, then you won't be able to tell. But if you reduce the number of people to 2 people in the class, and then you ask, regardless, I'm not putting any constraints of any kind, okay? How many ways can we arrange birth dates, given there are 2 people in the class? Then you go like, okay, the first person can choose any one day out of 365 days, and the same applies to the second person, any one day of the 365 days. So the total number of ways that 2 people can have birth dates, the way they can arrange to have different birth dates, not different. The way you can have 2 people to have birth dates would be 365 to the power of 2, or 365 squared. So that is what happens when you have with replacement. You're basically just raising the cardinality of the outcome set to the number of trials in the experiment, and that will give you the total number of ways that things can happen. Alright, so let me check out the text here. It was the example that was like the homework. Yeah. Great gift for a non-CISP440 person. I'm guessing that's a lotto ticket. It really makes me wonder, when people do get the jackpot, how many identical tickets are getting the jackpot. Because I think that's very likely to happen, is to have multiple tickets getting the jackpot. All right, so I hope this helps, with Armand's original question of, how do we distinguish when to use which way of computing stuff. Yeah, so let me check the time. Oh yeah, we are already out over time, but I do want to give you one more thing. The first one does give you a probability, so when you apply the binomial distribution thing, it does give you a probability. Okay, it give you a number. It will give you a number that is less than 1. So it is a probability to begin with. Now, the other two would not give you a probability. It will give you a count. It will give you a number of ways of blah, blah, blah. So it is not a probability by itself. So now the question is, you have to think about what is the cardinality of the event set, and then you have to ask what is the cardinality of the omega. So in the case of Lotto, okay, so if you're thinking about Lotto, okay, so I'm just gonna extend a little bit here to get back to the Lotto problem. The numerator is the cardinality of E, which is the event set, right? So in that case, let's just not take the Powerball into consideration. So in that case, we have 69 numbers to choose from, and out of the 69, we are choosing 5. And ordering is not important, and that's why we are using choose, because choose, the way you can remember whether choose is permutation or combination is they both start with the letter C. Okay, choose and combination, they both start with the letter C. So choose is giving you the number of combinations. So in this case, 69 choose 5 is going to be the denominator. Okay, I misspoke here. Denominator. There we go. All right. So now the numerator depends on which price are you talking about, right? Do you want 5, all 5 numbers matching the 5 lucky numbers, or do you want 4 matching and 1 is not matching, or 3 is matching and 2 is not matching? So instead of using the extreme case, which doesn't really illustrate how we do things, let's think about the case where you say, okay, I want to think about all the different ways that I can win, where I have 3 matching numbers and 2 non-matching numbers. So in that case, this is not omega anymore. This is not E. This is actually our omega. So now we're looking at the cardinality of the event set. So the event set in this case, since I just said 3 matching and 2 non-matching, so now we have to look at the first one is how many lucky numbers are we choosing from? There are 5 numbers that are already chosen, and out of those 5, I need 3 of them matching. So now we have 3 choose 2, and then and then you always have to remember on a ticket there are 5 numbers, and we have just accounted for 3 of them. There are 2 additional numbers, so those 2 additional numbers are coming from 69 minus 5, which is 64, choose 2. Because we have 64 non-chosen, or the non-lucky numbers, and out of those 64 numbers, we need to choose 2 of them, because otherwise we won't end up with 5 numbers on the ticket. So that's how we approach these problems. Is you have to look at the set of omega. Most of the time we don't really care about the set itself, but we do want to know what is the cardinality of the set. So in this case, the cardinality of the set itself of omega is by itself also a combination. And then when you look at the numerator, in this case, it is a product of 2 combinations, because we have to choose certain things from a subset, and then we have to choose the rest from another subset over here. And that's why it is multiplied, because for each way of choosing 3 of the 5 lucky numbers, it can be paired up with any way of choosing the 2 of the non-lucky numbers, and that's why they are multiplied and not added, because it's basically a tree. So you're basically looking at the first few levels of the tree of certain of a certain nature, but then all the subtrees after that are the same. So that's why you have to multiply and not add the two numbers. Alrighty, so we are out of time. You might have 4 numbers right, but then your chances diverge by the 5 numbers as well. Okay. Alright, so we are out of time. It is office hour now. I am still online, but I think I can stop the screen share unless there are additional things that you guys want me to demonstrate. Okay. All right. Cool. So I'm gonna turn off screen share and live stream, but I will stay online in the text channel. So if you guys have any additional questions, just gonna drop me a line over there.